Hi, welcome to Algebra 2 Common Core. Tonight we're going to talk about annual growth rates. We're going to start with exponential functions. So you should recall that exponential functions are functions that have the equation y equals a times b raised to the x power. Now let's take a look at that a value. Recall that a is always going to be our initial value. If it's a population, then it's the population that we are starting with. If it's money, it's the amount of money that we are starting with. It's always the value when our time is equal to 0. So the initial value. B stands for the growth or decay. If I have exponential growth, then of course my b value will be greater than 1. Remember then that my equation, y equals a times b, remember we replaced with 1 plus r to the x power. So the b value is this value right here, the 1 plus r. If I have exponential decay, that's when the b is greater than 0 but smaller than 1. So in that case, my equation looks like this. Y is equal to a times 1 minus r to the exponent of x. So in this case, my b value is equal to 1 minus r. That will allow us to solve for the r value. So let's go ahead and analyze some exponential functions. We had some exponential modeling earlier in this unit, but for this one we're going to call P of t the population. So my function's written in terms of P of t is equal to 24,500 times 1.08 to the t over 5. So we want to be able to analyze what each part of this function stands for. Recall that the initial population is just my a value. So when I look at this equation, I see that the a value tells me that my population must have started with 24,500. Growth or decay, well, I'm going to take a look at the b. So when I see the b in my equation, I see that that b value is greater than 1. So that tells me that I must have a growth factor here. This must be a population that is growing. I know that because the b value is greater than 1. So we then want to figure out what is the rate of growth. So that's our r value. So remember that the b stands for, when I've got growth, 1 plus r. So that b, 1.08, must have a value of 1 plus r. So we want to solve for r, so that's as easy as just subtracting 1 from both sides of the equation, and I get that r is equal to 0.08. Now usually we're going to write our rate as a percent, so recall that to convert from a decimal over to a percent, I'm just going to move my decimal point over 2 places to the right and say that this is a rate of 8%. So the rate that we're talking about is an 8% growth rate. Now we're going to introduce a time element into this problem that we haven't seen before. In the past, we've always used our exponent of t standing for our time measurement. But you'll see this time that t is divided by 5. What that divided by 5 tells me is how often the rate is being applied. So in this case, we see that we have a growth rate of 8%, and that divided by 5 tells me that it's going to be 8% every 5 years. So my population will grow by a factor of 8% every 5 years. Let's do the same thing with example number 2. This time our population equation is P of t is equal to 175,000 times 0.96 to the t over 3. So when I look at this, I see, of course, that my a value is just that initial population, 175,000 people. This, instead of being growth, has to be decay, because when I look at my b value, I see that that b value is less than 1, so this has to be a decay problem. So b is bigger than 0, but it's less than 1. Now let's go ahead and calculate what the rate is. When I have decay, I know that the b this time is 1 minus r. So 1 minus r must equal 0.96. Now let's be careful with our signs here. We're still going to subtract 1 from both sides of the equation. So we get that negative r is equal to negative 0.04. Dividing both sides of the equation by negative 1, I get that r is equal to 0.04. So what that then tells me is that my rate is going to be 4% because I'm going to convert this over to a percent from a decimal, move that decimal point over 2 places to the right, so I see that the rate is 4%. So I have a decay problem where the population is declining or decaying by 4%. Now, how often is this happening? Again, I want to look at that exponent and say it's not just a t, so it's not every year. Instead, t over 3 tells us that it's going to be every 3 years. So my population is going down by 4% every 3 years. Now, why don't you pause the video and try to answer these questions on your own. Come back and see if your answers match what I have. Welcome back. The initial population should be my A value. So when I look at this equation, I see that the A value is 18,750. This has to be a growth problem because I see that my B value is a number that's bigger than 1. So I'm going to say exponential growth. If you're asked to justify that, it's a good justification to say that the B value is greater than 1. Now we wanted to figure out the rate. So to find the rate, since I've got growth, my B value is equal to 1 plus R. So the B value of 1.315 is 1 plus R. Again, subtracting 1 from both sides of the equation, I have that R is equal to 0.315. Now take that decimal point and multiply by 100 by moving it 2 places to the right. So that tells us that I've got a growth rate of 31.5%. So I'm going to put that down for my rate value. Now, how often? Again, remember, go up to that exponent, and t divided by 10 tells me that I have that growth rate of 31.5% every 10 years. So it's important to note that our growth rate or our decay rate is not always given to us as a yearly value. Now let's go ahead and try to build some of these exponential equations to model populations. So if I see that I'm starting with a population of 30,000 and I see that my population is growing, I'm given the rate and I'm told how often that happens. So let's set up our equation for P of t. So we start with P of t is equal to, our initial population has to be 30,000 for this population. Now, since I see that my population is growing, that tells me that to get my B value, I'm going to have to say 1 plus the rate of growth. Now, since the rate of growth is equal to 1.8%, let's talk about that as a decimal. So now going from percent to decimal, I've got to do exactly the opposite and take my decimal point and go 2 places to the left. So that's going to be 1 plus 0.018. So the B value that I'm going to put into my equation is 1.018. So that goes right here. And then, since my population is growing at that rate every 4 years, my exponent is going to be t divided by 4. So I hope you can follow along to see how these exponential equations are formed. Let's try building another exponential function. This time the population is 220,000, and I see that it's decreasing at a rate of 7% every 9 years. So starting with my equation, the easiest thing, of course, to start with is my population at the beginning. So 220,000. Now, since I've got decay or decreasing, I have to use my b value, which is going to be equal to 1 minus r. Now our rate of 7%, don't forget to convert that over to a decimal, so I've got to take the decimal point, move it over 2 places to the left. So b is equal to 1 minus 0.07. That tells us that for this decay problem, b is equal to 0.93. I expected a number less than 1 because I've got exponential decay. So that goes inside my parentheses, 0.93. The exponent, since I am decreasing at this rate every 9 years, we're going to say t gets divided by 9. So we've built this function as an exponential function. Now let's just take a minute to review some of our exponential rules. The one that's important for us today is when we're raising a power to a power. Remember that x to the third to the fourth power really means that I've got x to the third times x to the third multiplied by itself 4 times. Now, when I'm multiplying, I really add those exponents together. So x to the third times x to the third times x to the third times x to the third really is giving me x to the 12th. And remember back to the first day of our exponential rules, we said that all we really needed to do to raise a power to a power is multiply those exponents together. So looking at example B, we can take that shortcut and say x to the 1/2 raised to the 4t is just going to be x to the 1/2 multiplied by 4t. So remember that the 4t really is over a 1. So this is going to give me x to the 4t over 2, which is going to give me x to the 2t. So with our future examples, we're going to need to be able to raise powers to powers. So it's very important that we understand this rule. How about the last one? X to the 1/5 raised to the 5t. That really means x to the 1/5 times 5t. Now that 5t is, of course, over 1. So when I multiply those exponents together, I'm getting x to the t power. Now our goal in tonight's lesson is actually to be able to calculate an annual rate of change. What we want to remember is that the word annual means in 1 year or per year. So we want to be able to calculate what the rate of change is on a yearly basis. The most important thing to remember here is that in order to identify an annual rate of change, my t must have a coefficient of 1. So in the past we've seen some examples where we have other than 1 with the t. We might be either dividing by a number or multiplying by a number. But if we want annual rate of change, we have to make sure that our coefficient of t is 1. So looking at our first example, we've got p of t is equal to 2,500 times 1.04 to the t over 2. So for this problem, we'd like to calculate the annual rate of change, which means that we want to rewrite this as an equivalent expression, as an equivalent equation, exponential equation, where the exponent is just a t, so a 1t. So looking at our equation, we've got p of t is equal to, our original population, 2,500, isn't really affected in this process. When I look at this base, 1.04, I see that my exponent is t over 2. So I could also write that as 1/2 times t. Now I'm going to actually undo the examples that we did on the previous slide, where we say when we're raising a power to a power, we multiply those exponents together. So I can think of this as kind of working backwards. So I can say P of t is equal to, again, just keep that original population throughout the problem, and say we could really write this as 1.04 to the 1/2 raised to the t. So you'll notice that we've gotten to our goal of having just 1t as our exponent. So this number right here, the 1.04 to the 1/2, is really going to be our b value. I'm going to go to my graphing calculator, and I'm going to do that portion on my calculator, the 1.04 to the 1/2, so that I can find the actual value of b and calculate my annual rate of change. So P of t is equal to 2,500 stays. Now on my calculator, I'm just using the caret key, so I'm doing 1.04 raised to the 1/2. Now, when I do that, I get this new decimal, and yes, it kind of goes on, but I'm going to write down the first few digits, 1.0198. That's going to be raised to that t that I saw on the line above. So this new b value right here represents our growth when I have 1 year. So this b value, since it's growth, is equal to 1 plus r. Let's calculate our r value. So if 1 plus r has to equal 1.0198, subtracting 1 from both sides of the equation, I see clearly that r is equal to 0.0198. I'm sure some of you can now just look at that expression and be able to tell what your r is. We want to convert that over to a percent, so let's take that decimal point over 2 places to the right, and we see that our rate of growth on an annual basis is 1.98%. So this is the rate per year. Because it's per year, that's going to be called our annual growth rate. So that's what we were looking for in this problem. If my population was growing at a rate of 1.04 every 2 years, I wanted to calculate what was the growth rate per 1 year. You'll notice that we didn't just take that expression, 1.04, and divide by 2. Instead, we had to raise it to the 1/2 power, and that's because of our rules of exponents. Let's try another example of finding annual rate of change. So my equation P of t is equal to the original population, 725. For this one, I see that t in my exponent is being divided by 6. So I can rewrite that as 1.16 to the 1/6 t. It's exactly the same thing as t over 6. What does that allow me to do? I can move that divided by 6, or the 1/6, in as an exponent on the 1.16. There's a lot of 6's in this problem. So now I'm going to go to my calculator and calculate, keep that 725. So in my calculator, I'm putting in 1.16 raised to the 1/6 power. That's giving me 1.025 raised to the t. I like that idea of having an exponent of t because that tells me that I am finding the annual rate of change. Annual because I have just one t. So let's go ahead and calculate our r value. This again is growth, so 1 plus r must be equal to 1.025. Again, subtracting 1 from both sides of the equation, I get that r is equal to 0.025. Convert that over to a percent, so move your decimal point over 2 places to the right, and I see that it turns out to be 2.5% per year. And that's what I wanted to find, the percent change per year, so that I'm finding the annual rate of change. Let's try one more of these annual rates of change. If you're feeling pretty confident, pause the video and try it on your own, and then come back and see if yours matches mine. So my function p of t would be equal to the initial population 1500. You'll see that my b value right now is 1.29, but that's when I have a growth rate every 12 years. I'm going to move that 1/12 inside as an exponent on the 1.29 and then raise to the t power on the outside. Going to my calculator, I see that p of t is just equal to 1500. On my calculator, 1.29 raised to the 1/12 is giving me a new decimal, 1.0214, and yes, it does give me more places there, but I'm just going to go with about that many. Raised to the t. This again is a growth rate, so I'm going to say 1 plus r is equal to 1.0214. So when I subtract 1 from both sides of the equation, I get that r is equal to 0.0214. When I convert that over to a percent, let's call that 2.1% per year. And that, of course, is my annual growth rate for this population. Now for our last example, we're going to have the biggest challenge of the night. We're given some information, so we want to first of all start by building our exponential function. It says that we have a population of 45,000, so we're going to start with our p of t at our initial population of 45,000. It happens to be a growth problem, and I see that my rate of growth is 20%. So that tells me if I convert my r over to a decimal, 0.20. So my b is going to be equal to 1 plus r. So b is equal to 1 plus 0.2, or 1.2 as the b. Write that inside of your parentheses, so 1.2. Now, this is the growth rate every 10 years. So that tells me to make my exponent t divided by 10. Now what makes this problem a little more difficult is that I'm not asked for a percent growth rate for the annual time period. Instead, I'm asked for a 3-year time period. Unfortunately, it's very difficult to go directly from a 10-year rate to a 3-year rate. So I'm going to take an intermediate step, and I'm going to first of all find the annual growth rate. So to find the annual growth rate, we've been doing those in the last few examples. So we say p of t is equal to 45,000. I've got my 1.2 as my b value. And because my exponent is divided by 10, I'm going to move that 1/10 to the inside. And now I'm raising my base to a t, which tells me I'm going to have the annual growth rate. Let's go to your calculator. So I've got the p of t is equal to 45,000. When I raise 1.2 to the 1/10, that's giving me 1.0184, and that's raised to the t. So this becomes our annual growth rate. This is our equation representing the growth rate in 1 year. Now we want to switch over and we want to now say, how about if we want to find the 3-year growth rate? Well, the 3-year growth rate means that we have to have as our exponent a t divided by 3. But we can't just go ahead and divide by 3. We've got to think about how we write it as an equivalent expression. So I've got 1.0184. I want to end up with t over 3, so to make sure that I'm balancing out that 3, I'm going to also multiply by 3. I want to end up with t over 3 as my exponent on the outside, so this extra factor of 3 becomes an exponent on the inside. So I'm going to say p of t is equal to 45,000. Take my 1.0184 and raise it to the 3rd power, and then keep the exponent of t over 3 on the outside. Notice that I haven't changed how I'm writing. I haven't changed the value of my expression. I'm just changing how I'm writing it. Let's simplify this equation. So we're going to say P of T is equal to 45,000. And when I go to my calculator and do 1.0184 to the third power, I got on my calculator 1.056. And again, that exponent is T over 3. That's what I wanted because I wanted to know what the growth rate was over a 3-year time period. So now we need to take a look at this B value. Again, I see that it's greater than 1, of course, so I've got growth. So 1 plus R must equal 1.056. So therefore, subtracting 1 from both sides of the equation, I see that the R is 0.056. Convert that to a percent. Move your decimal point 2 places to the right. So that tells me that over 3 years, my population is growing by 5.6% every 3 years. Now, we've covered a lot of ground tonight, and this is one of the more difficult topics, so please make sure that you understand each of the examples that we've done, but we'll be practicing this a lot more in class tomorrow. So if it's a little hazy at this point, that's okay. We'll be looking at more examples tomorrow. Have a great night, and we'll see you in class.